by the Dendrimer reactor. Third one, the synthesis and the catalysis of the multi-metallic particles. Okay. So as you know, nanometal particles deserve much attention because of the wide applications. Many nanometal particles have been synthesized, so many researchers are developing on the new synthetic method and the new function of the nanometal particles. However, few papers reported on the sub-nano-size metal particles, which are about 1 nanometer diameter, because it is very difficult to synthesize a sub-nano-size metal particle with well-defined structures. So we have not yet precisely controlled the number of the atoms in the sub-nano-size metal particle. So therefore, the sub-nano-size metal particle with several kinds of elements, so-called the sub-nano heterometal particle, are classified as new substances. So I think the synthesis of the sub-nano heterometal particle will open up a frontier in the field of the material chemistries. So objective of our study is synthesis of the multi-metal particles to make a precision combination of the multi-elements. So we call the atom hybridizations. So my curiosity is how many kinds of the elements can be combined in the sub-nano-size metal particles. So why should we pay attention to the sub-nano-size metal particles? So in the nano regions, as you know, the properties of the nanometal particle are dominated by the surface area effect. In contrast, the sub-nano region, the property of the sub-nano-size metal particle dominated by the quantum size effect. So by decreasing the number of the atoms less than 30, the orbital generality is resolved. So the electron state drastically changes with atomicity. So the properties of the sub-nano-size metal particles drastically changes with atomicities. So we expect quite different properties, functions, activities of the sub-nano-size metal particle in every number of the atoms. So they are very attractive and interesting material. So this is the motivation to investigate the sub-nano-size metal particles. So I would like to introduce a very interesting report on the sub-nano-size metal particles. Aluminum particle with 13 atoms does not show the original property of the aluminum, but that of the halogen. So which called the super atoms. So when the property of the sub-nano-size metal particle drastically changes from the original element to the another element, so it's called the super atoms. However, so super atom has not been synthesized as a material until now. So as you know, we have 118 elements in the period table. So there are infinity of the combination of the metal elements. So we expect the generation of the inexhaustible new nanomaterials. So we should establish a precision synthesis of the sub-nano-size metal particles. In the current chemistry, it's very difficult to synthesize the sub-nano-size metal particles. So generally, random products are produced by the conventional method in the presence of several kinds of element salts. So resulting sub-nano-size metal particles have a wide distribution of the composition in the sub-nano-size metal particles. So we would like to propose the new approaches for the formation of the fine control of the sub-nano-size metal particles. Molecular reactor, which enable to determine the number of the atoms, is important for the formation of the fine control of the sub-nano-size metal particles. After assembling the metal salts precisely in the molecular reactor, So reduction or oxidation carried out. So we can obtain the subnano-sized metal particles selectively. So molecular reactor is important for the formation of the fine controlled subnano-sized metal particles. So I move on the Dendrimer reactors for the multimetallic particles. So we focus on the phenylazomethyl dendrimer. So these structures, so C and double bond, imine bond act as excellent coordination site for the metal assembly. So this type dendrimers have a 30 imine unit as a coordination site. So this polymer is a typical polymeric reagent. So we synthesize the phenylazomethyl dendrimers, these structures. So this dendrimer shows a very unique complexation behavior. So we carried out complexation of the tin chloride with dendrimers. So during a titration, so 400 nanometer increase with decreasing absorption at around 300 nanometers, which is attributed to the T and double bond. So interestingly, so spectral changes with isophase point. For 0 to 2 equimolar amount of the tin chloride addition, isophase point was of the 375 nanometer. 2 to 6 equimolar amount of the tin chloride addition, isophase point was of the 364 nanometer. 6 to 14 equimolar amount addition of the tin chloride, isophase point at 360 nanometers. 14 to 13 equimolar amount. So isophase point at 355 nanometers. So it's very interestingly, complexation proceeds not at random, but a stepwise fashions. So we first stepwise complexation of the metal salt in the dendrimer. So what meaning is the stepwise complexations? So during a titration, 4 changes in the isophase point were observed. After by adding the 2 more equimolar amount of the chloride, isophase point was shifted. By adding the 4 more equimolar amount of the tin chloride, isophase point was shifted. By adding the 8 more equimolar amount, isophase point was shifted. By adding 16 more equimolar amount, subspectral saturated. 2, 4, 8, 16. These numbers are corresponding to the number of the imine unit in each generation layers. 2, 4, 8, 16. So interestingly, complexation proceeds not at random, but a stepwise fashion from the forward to the periphery, shown in this animation. Of course, kinetically, so metal salt first coordinates the periphery of the dendrimers. Spectra measured under the equilibrium conditions. So thermodynamically, metal is assembled from the core to the periphery, shown in this animation. So we call this behavior stepwise radial complexation. So this behavior is very important. So because we can control the number and the location of the metal salt in the dendrimers. So until now, we have already synthesized more than 30 kinds of the dendrimer reactors. The core structures, phenyl group, phenyl metal core, phenyl cores, and toluene core, and so on. Okay, I move on the control of the assembling order of the metal salts. So in order to control the assembling order, we synthesize the phenylazomethyl dendrimers with fluoride group as a core. As you know, fluoride group is an electron withdrawing group. So this dendrimer shows 3 changes at which point on the basis of the spectral changes. So first, metal is assembled at the second layer, which hold imine. Next, metal assembled at the third layer, which has 8 imine. Plus, metal is assembled first layer. Second layer, third layer is the first layer. So introduction of the electron withdrawing group results in a changing the assembling orders. So we designed the dendrimers which shows reverse metal assembly from the periphery to the core side. So we synthesize phenylazomethyl dendrimers with metal link. So this dendrimer has a non-conjugate structure. So the electron density at the periphery is higher than that of the core structure due to the electron induced effect of the isometric group. So this dendrimers metal salt first coordinates the third layer, next is the second layer, the first layer. So we can control the number, we can control the order of the coordination behavior based on the structure of the dendrimer reactors. So recently we found very interesting dendrimers which show the very unique complexation behavior. So we synthesize the phenylazomethine dendrimers with pyrazine unit at the core. This dendrimer has an asymmetric structure. So during a titration, the 9 changes isophase point were observed. So equimolar of the metal salt for the shift of the isophase point is 1, 1, 3, 2, 6, 4, 12, 8, 24. So we can control the number of the metal salt more precisely based on these numbers. Okay, so we carried out synthesis of the we carried out the metal assembling the metal salts, various metal salts in the period table. So most of the metal salts show the stepwise radial complexations. So we can control the number of the metal salt in the dendrimers. So we succeed in assembling the various metal salts using the 67 kinds of the elements shown in these figures. So as you know, there are 81 stable elements in the period table, excluding the rare gas and toxic elements. There are 70. So 67. So we have completed metal assembling, so using the stable and the practical use elements shown in these figures. Okay, next is the heterometal assembling of the metal salt. We carried out the heterometal assembling using the dendrimers with pyrazine unit at the core. So different kinds of the element salts were added in each step. So we could prepare the heterometal dendrimers shown in figures. So we succeed in the heterometal dendrimers with 10 elements. So we have also prepared the heterometal assembly structure more than 150 patterns using the dendrimer reactor. Okay, I move on the synthesis of the subnanosized metal particles. So we have an excellent molecular reactor. Phenylazomethine dendrimers shows the stepwise radial complexation. So we can control the number of the metal salts in the dendrimers. So we developed the synthesis of the subnanosized metal particles using the dendrimers. After the assembling the metal salt precisely using the dendrimers, so reduction or oxidation is carried out. So we can obtain the subnanosized metal particle. So with fine controlled structures. So we synthesize many subnanosized metal particles using the dendrimer reactors. So after the assembling the metal salt, reduction of the metal dendrimers carried out. So we could obtain the subnanosized particle of the 30 kinds of the elements shown in these figures. Okay, so next is the synthesis of the multimetallic particles. I have already mentioned, so the different kinds of elemental salts were added in each step. So we obtained the heterometal dendrimers. So after reduction of the heterometal dendrimers, we can obtain the multimetallic particles. So we succeed in the multimetallic particle with 6 elements using the dendrimers. So the resulting the subnanocyte metal particle have a gallium, indium, gold, bismuth, tin, and platinum. 6 element is the maximum number in the subnanocyte metal particle until now. Okay, so next I move on the catalyst of subnanocyte particle for the oxygen reductions. We carry out the synthesis of the subnanoplatinum particle using the Dendrimer reactors. Platinum chloride was used as a salt. So platinum chloride shows a stepwise areal complexation. So we can control the number of the platinum chloride in the dendrimers. So platinum chloride in the dendrimers is easily reduced to the zero valence state platinum using the sodium hydrochloride. Okay, we carried out a chemical measurement for the catalysis of the platinum subnanocyte particles. So the modified electrodes were prepared by the casting of the solution of the platinum particle encapsulated dendrimer on the electrode surfaces. We have monitored the reduction current of the oxygen under the oxygen atmosphere in the cyclic photometry and the rotating disk photometries. So we summarize the catalytic activities of the resulting subnanocyte metal particle for the oxygen reduction. The catalytic activity is normalized on the basis of the commercially available one, so about 2 or 3 nanometers. So interestingly, catalytic activity increases, decreasing the number of the atoms. So especially platinum particle atom shows 13 times larger than that of the commercially available one. So subnanocyte platinum particle act as an excellent catalyst for the oxygen reductions. Okay, so last topic is we demonstrated one atom controls the synthesis of the subnanocyte particles. So platinum particles, 12 atoms, and 13 atoms. So we prepare the platinum particle with 13 atoms using dendrimer with pyridine unit as a core work. So this dendrimer has a 148 coordination site, totally it's 13 coordination site. So we could prepare the platinum particle with 13 atoms using this dendrimers. So we prepare the platinum particle, 12 atoms, 13 atoms. This figure shows the STM images of the resulting subnanocyte particles, 12 atoms, 13 atoms. Of course, we could not distinguish the size of the platinum particle between the 12 atoms and 13 atoms. However, so we zoomed in the one particles. So we succeed in the observation of the platinum atoms moving structure. So we could count number of the platinum in the particle. This particle has 12 atoms. This particle has 13 atoms. So we prepare the platinum particle, 12 atoms and 13 atoms selectively. So in order to elucidate the structure for the more detail, so we carried out ESI tougher spectroscopy. So we carried out ligand exchanges from the dendrimer framework to the carbon monoxide. Because the dendrimer framework is too large to observe the fragment in the ESI tougher spectroscopies. So after the ligand exchange to the carbon monoxide, so in the ESI tougher spectroscopy, single fragment peak were observed, which attributed the platinum particle 12 atoms and 13 atoms. So we succeed in the synthesis of the subnanocyte particle. So with 12 atoms, 13 atoms selective. Okay, I show the interesting catalytic activity of the platinum particles. So we compare the catalytic activity between the platinum particle 12 atoms and 13 atoms. So interestingly, the platinum particle with 12 atoms shows a 2.5 times larger than that of the platinum particle with 13 atoms. So this result indicates a significant conclusions. So one atom difference resulting in a significant difference in the catalytic activity. So we should check the catalytic activity of the subnano-sized particle in every number of the atoms. So we have confirmed the catalytic activity of the platinum particle in every number of the atoms between the 12 and 20s. So platinum particle with 19 atoms shows the largest catalytic activity in this subnano-sized platinum particle. So we found platinum particle with 19 atoms acts as excellent catalyst for the electron reduction of the oxygen. So until now, we have already so many subnano-sized metal particles. So subnano-sized metal particles are applicable to many reactions as a catalyst. Aerobic oxidation of the alkane, so reductive amination, so formation of the carbon nanotube, hydrogenation of the alkane, and reduction of the nitrogen group, and the reduction of the oxygen, and so on. Okay, so conclusion. So we carried out metal assembling. So we succeed in the accumulation of the so we succeed in the accumulation of the metal salt. So using the 67 kinds of the elements. So we succeed in the formation of subnano particle with 6 metal elements. So that the catalytic activity of the subnano-sized particle were confirmed. So in every number of the atoms, so platinum particle, subnano-sized platinum acts as an excellent catalyst for electron reduction of the oxygens. Today's talk I have already published as a review, so in the chemical review, Nature Review Chemistry. So if you're interested, please. So last slide. I would like to express my thanks to my colleague in my laboratories. Thank you for your kind attention.